All right, so let's get started. I'm a little out of focus, so. Yeah, a little out of focus. All right. So saw a pretty broad swath of answers. I didn't get homework from everyone. Certainly not from everyone. But the idea here is the limit as h approaches 0 of f of x plus h minus f of x all over h is equal to the first derivative. Now, so for the two homework problems that you had f of x was x plus 1 all over x plus 2. So rather than writing all of these out again, I'm just going to give you the answer. So f of x plus h means you replace x with x plus h. So if the function was x plus 1 all over x plus 2, plugging x plus h in every time you see x gives you this, and then the function itself. And then getting a common denominator, multiplying out all of your terms, distributing the negative and combining like terms leaves you with only those two, which reduces to 1h and then reduces with the h. And then when I take the limit, h goes to 0 and I have x plus 2 quantity squared. Many of you did multiplied out the denominator too, and your answers therefore look like x squared plus 4x plus 4. Okay, some people did not know how to plug in this term correctly. Okay. And you know, like that kind of scares me a little bit too. All right. So now the second one, you had to find the derivative of the derivative. You had to find what is called the second derivative. Okay. So taking the function, which was 3x cubed plus x squared, and this was your f of x. Okay. Plugging in x plus h every time you see an h, every time you see an x gives you that minus the function itself. Expand this out. Expand out the second one, distributing the negative sign. Now, distributing the 3, so the 3 goes to the x cubed, which cancels out with that one. This 3 goes to that term. There's no other term to cancel with, so it stays where it is. This distributes there. This distributes there. This x squared gets eliminated with that x squared, leaving me just this one, and there they are. All terms contain an h, so I can reduce that. And then when I take the limit as h approaches 0, this term goes away, so does that, and so does that, leaving me with just 9x squared and 2x. Now, taking the derivative of this, plug in x plus h everywhere you see an x. Function notation, ladies and gentlemen. All right, now expanding that term, And obviously I just, I have distributed the negative there. I mean, I can show that piece, but, it was that. Distributing the negative, distributing the 2, expanding. Now the 9x squared cancels with that 9x squared. 9 times 2xh becomes 18. 9h squared. 2x goes away with the negative 2x, leaving me just a 2h right here. All terms contain an h. And that's kind of the clue that you're on the right track. If all of your h's in if your h in your denominator goes away, and you're left with this, and then when h goes to 0, that goes to 0, and you're left with 18x plus 2. Okay. Questions, issues, moans, whines, or complaints? Okay. All right. So if I gave you and I'm just going to do this for myself. All right. So if I told you that this was the limit as h approaches 0 of x of x plus h minus f of x for some value of c, for some f of x and some value x equals c. So I have a function, which I'm not telling you what it is. And I'm telling you that I'm evaluating it at c. And when I do that, I get this. Find f of x and find c. Take a few minutes and think about that. Answers. So if the square root of 4 plus h is equal to some function of x plus h, that tells me that, and I also know that 2 is equal to f of, I'm sorry, this shouldn't be x, this should be c. F of c, all right? This tells me that 4 plus h, well, first of all, this tells me right away that the square root of x is your f of x, and c is equal to 4. And I can confirm that by plugging that in and seeing that, in fact, the square root of 4 is 2. Okay. So now let me ask you a similar question. Find f of x and find c. Okay. So I've gotten one right answer, and I think a bunch of you guys are chasing your tails. So here's how here's how you do this. I told you that I've already found the common denominator. So if this is supposed to be f of x plus h minus f of x, all right, break it up. And of course, I don't really care about the limit part or the denominator. I just care about the numerator right now anyway. All right, you want to try one more? All right. Let's do yeah, so in this one, c is not a constant. Sorry, x is not a constant. It's just a function. So you don't have to worry about finding the c. Just find the function f of x. How are we doing, ladies and gentlemen?
Absolutely fabulous.
Fantastic. Okay. All right. So I'm going to use two properties of the real numbers and then one thing from your notes. And now this is, if you look very carefully, cosine, 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 sine is the sine of x minus h minus the sine of x. So f of x is sine of x. Okay, but in fact, this allows us to come up here and do an important thing. So let's do this one more time. This brings up an important point. So if I have the sine, let's not do sine first, let's do cosine. So if I'm taking the derivative of cosine, the limit as h approaches 0 of the cosine of x minus plus h minus the cosine of x over h. So what I'm going to do is I'm going to go ahead and I'm going to expand this, and I get cosine of x, cosine, cosine, minus sine, sine, minus cosine of x. Okay. So now what I'm going to do is I'm going to do what I did a moment ago. and group together the two cosine terms. And I'm just going to go ahead and put them both over h. Now, if you remember when we were doing limits, we saw this all the time. Remember that? Does anybody remember what it equaled?
1.
And we saw this. Does anybody remember what that was?
Zero.
And there you have them. So now I can say that this limit is 0. And sine h over h is 1. So the derivative, if f of x is equal to the cosine of x, the derivative is negative sine of x. And sometimes you'll see it written this way: cosine of x prime, or the derivative of this, is equal to negative sine of x. Now I want to talk about notation, but I'll get to notation in a minute. I want to do the derivative of sine. All right. So the limit as h approaches 0 of the sine of x plus h minus sine of x all over h. Sine, cosine, cosine, sine, minus sine. Now, collecting my sine of x terms, wait, plus, this is minus. Wait. Sine, cosine, cosine, sine is plus. This is plus. Now, using the same thing, this is 0, and this is 1. So the derivative of sine is the cosine.
Mr. Ronco,
Speak to me.
for the cosine one, isn't it backwards though? Like, isn't it normally cosine x minus 1?
Where? Oh, but it doesn't matter. It goes to 0. So it's negative 0. Right? And we can see those just to show you. I wanted to visually show those to you really quickly. screen share. This one. You guys looking at GeoGebra screen? So here's sine of x over x, and you can see that the limit goes to 1. Let me see if I can get my font size a little bigger. There we go. So the sine of x over x goes to 1, and the cosine of x minus 1 over x goes to 0. And if this was backwards, it would just be flipped upside down. But that's the only difference. But it still goes to 0. Okay. And if I did that, like I said, it just flips it upside down, but it doesn't change the function's limit. All right. Okay. Now, do you dare try finding the derivative of tangent? All right, let's do tangent together. It's going to be a hot mess, but we'll do it anyway. Well, later on, there's another way of doing this, which makes it a much simpler. All right. And you know what? For time's sake, we'll do tangent later when we learn some other tools. But you can do it by the limit process, but I'll just say that it sucks. It's just not a lot of fun. All right. But we'll get there. Okay. So now just a matter of notation. Okay. We can write a derivative as using, this prime notation. Okay. But this is useful in some places. Okay. It's kind of a mathematical shorthand for saying this. The derivative of a function with respect to x. Now this, sometimes you'll see it written as dy dx. Now this is, the language is important. This is, first of all, this is what is called Leibniz notation, or Leibniz notation. Okay, depending on how much German you know. Leibniz notation is very, very useful, especially when we get into higher forms of calculus. And really what this is saying is I have an incremental step in y and an incremental step in x. Okay, so what's happening here, if I can allow you to, if I can be allowed to zoom in. When we did this the other day, we saw this kind of an effect. I had x plus h. This is f of x, and this was f of x plus h. Now, Now, we were trying to find the tangent. We were trying to find the slope of the tangent line. And what's happening here is that as h gets smaller, this also gets smaller. And what's happening here is that this h is actually a small change in x. And this is your change in y. Now, if you go back to the idea of a slope, the slope is defined as the change in y divided by the change in x. That is what slope is. But what we're doing is we're making this delta x, this h, which is the same thing as saying x plus delta x, or f of x plus delta x. Same thing. We're making this delta x infinitesimally small. And this delta x now really doesn't do it justice. This is a non-zero number, okay? This is a discrete change in x and a discrete change in y, meaning that I could measure them. If I set delta x equal to 0.2, I could find out what the delta y is, okay? But when I take the limit of this and delta x gets infinitesimally small, it is no longer discrete. It's no longer measurable. Instead, it has to be infinitesimally small. And it gets so small that it approaches zero. And this is what the problem was with calculus for almost 100 years. Calculus was originally developed simultaneously between two men living at the same time, obviously. Wilfried Gottlieb Leibniz and Sir Isaac Newton. Now, Leibniz used this notation, whereas Newton used this notation. And very rarely, and you can, if you know somebody that has studied mathematics in Asia, okay, preferably on the Indian subcontinent, they still teach this. Because you have to remember, India was a British protectorate up until the 50s, okay? And there, I mean, if you go to India, and I don't know if anybody's ever been to India, a lot of people speak English as well as Hindi and other languages. And the language of academia is English. But Isaac Newton was English. Leibniz was German. And for a long time, English mathematicians used specifically Newtonian notation for calculus. And since India was a British protectorate, you still see Newtonian mathematics, Newtonian symbolism in the universities in India. And if you're ever interested in seeing that just for cool, just to see it, look up IIT videos in calculus. IIT is the Indian Institute of Technology. And it's basically their version of MIT. Okay, it's like the super smart math and science school for a country of 1.3 billion people. And there are many of these. There's like many campuses in like all the major cities and have one of these campuses, and they're incredibly good. I visited one, and I have a friend of mine who went there. And I'll tell you that it's very cool to see calculus being done using this notation. It's kind of neat. But anyway, the rest of the world has developed and used this. And also I will say that Indian mathematics also uses this when it's necessary. Occasionally you'll see physicists use this. Sometimes use this, but they are probably very old physicists. Okay, modern physicists don't use this very much. Okay, but anyway, so what we have is what is called the differential operator. Why don't we use it? Emma asks, it's a good question. Because first of all, I mean, it is an interesting question. We found using later forms of mathematics, when we start doing some other branches of calculus, that this notation becomes much more useful to us. Because what we're going to wind up doing later on down the road is breaking this up into a numerator and a denominator and treating them differently, whereas this is only one symbol. Now, the other thing that also makes this more useful is sometimes we're not dealing with x and y. Sometimes we're taking a derivative with respect to time, or how does something change in time, or if we're dealing with x, y, and z, in 3 dimensions. This doesn't, if I wanted to say take a derivative with respect to time, I might see dy dt. And in the same problem, there might be dy dx. So the question is, which one is this talking about? Is it talking about with respect to time, or is it differentiating with respect to x? And so this is not so much as useful as that is. But we have what is called the differential operator. And the differential operator is this, and it's being treated on this. So what this is saying is the derivative of f of x with respect to x. So let me just put that in there. This is how you would say it. Now, we're using this phrase with respect to x. So what I want to describe to you is that this concept of with respect to means as x changes. Okay, so let me give you an example, and we're not going to solve this today, but I just kind of want to introduce you to the idea that you can be taking a derivative with respect to other things. All right, we're going to see this problem down the road, so don't worry about it right now. This will be coming in like 2 weeks or something. Okay, let's say I have a building, and leaning up against the building is up against the window is a ladder. And just for, and, this is just my crappy illustration of a house and a ladder. Okay, but you get my point. Okay. Now, let's say that the ladder is 20 feet long. Okay. And this is 16 feet high. Okay. And this is 12 feet away from the, so I've got, a 3, 4, 5 Pythagorean triple, right? Okay. So I got a Pythagorean, a right triangle. Now here's what happens. All of a sudden, it starts to slip. Okay. The base of, now hopefully there's nobody standing on here. But as it starts to slip, several things are happening. This height is falling. So now I'm going to draw a lousier picture. We can all imagine what he's saying. So this is falling. This is falling, is sliding. And this angle is changing, this angle theta. And all of those things are happening at the same time. Does that make sense? Visually, do you see what we're doing here? Thumbs? Okay. Now, I can describe the change in y as x moves away. So this would be how for every step that the ladder slides, the top of the ladder falls by how much. Okay. And I can also say, how much does the angle change for every step of the x changing? I could also say, how fast is the ladder sliding? Because let's think about this. This is important. This is a real big deal. This is the change in y divided by the change in time, or change in x, sorry. Change in time. How much am I moving in a certain amount of time? This is speed. And for those of you that have ever taken physics, you know about this term velocity, right? And there's a difference between speed and velocity, but the point is that if you take a physics class with calculus, this is how you describe speed using calculus. How much does something change in a certain amount of time? Think of miles per hour, feet per second. I could also describe how fast is the ladder fall, or how fast is the angle changing, or how fast is the ladder falling. These are all different speeds. These are rates. If you give me a foot, how far will I fall? You see, these are not speeds. These are relationships. If you remove a foot, how many degrees will this change? You see what I mean? So when we say with respect to, what we're saying is when it, or when with respect to, you know, let's call it P, when P changes. That's basically what it says. So how does something change with respect to P, whatever P is, time, X, angle? I could even do, you know what? I could even make another relationship and say dy d theta. For every degree of angle change, how much does this fall? Or d theta dy. How much does the angle change for every amount of unit that the y falls? Okay. So this is the idea when I'm saying with respect to something. Okay. Have I completely lost you all? All right, give me a scale of 1 to 5, how we're feeling about all this mess. So this is all notation. This is all language. We're going to learn all of these one after the other after the other. We'll have plenty of time to learn all of this because we're not going to get as far this year as we will, because we're going to do it more next year as well. All right. So all right. So now let's just do some other problems just for giggles. X cubed. How am I phrasing this? Find the equation of the line, or find the value of X. Okay. So in order to do this problem, we have to understand what's being asked of us. I've got this function, a cubic function. It looks like that. And I want to find a tangent line. Well, I want to find which value of X gives me a tangent line that's parallel to this line. So the first thing we have to do is find the slope of this line. Because remember, parallel lines have the same slope. You guys remember that from geometry? So what is the slope of this line?
Three.
Right. Because 3x minus 4 is equal to y. So 3 is your slope. So now what you have to do is find the derivative of this and find out when it has a line, sorry, when it has a slope of 3. You think you can do that? Give it a try. All right, so that's the derivative, and this is the slope. Okay, and the question is when is the slope 3? So 3x squared equals 3, x squared equals 1. So x is equal to, or x is an element of the set 1 and -1. Because you have to remember both of them. Okay. You want to try one more? All right. This one's trickier. Wait, want to make that a plus. So the first thing you ought to do is get rid of this exponential notation. Turn it into something more reasonable. All right, just so that we can deal with this and be done, the bell's about to ring. There you go. So that's your function. Sorry, well, that's your function, and that's f of x plus h. Get a common denominator. Bring the h up, you get that. Rationalizing the numerator. Distributing this out is the difference of squares. Distributing and simplifying. And then I take the limit as h approaches 0. This goes to 0, that goes to 0. And I get the square root of x times the square root of x, square root of x plus the square root of x. X square root of x times the square root of x is x. And so I get -1/2 x square roots of x. And this is supposed to equal the slope of that line, x minus 2y is equal to 6. And you wind up with x minus 6 is equal to 2y. 1/2 x minus 3 is equal to y. And so I need a slope of 1/2. Okay. Was it minus y or plus y? It was plus y. Oops. So that's a minus, and now that's a minus. So -1/2 x square roots of x is equal to -1/2. So 1 all over x square roots of x is equal to 1. So x square roots of x is equal to 1. And x is equal to 1. And you're done. Okay. All right. So the bell is rung. Class is over. I will see all of you next week. I will be emailing you a homework assignment, and it is lengthy, and I want it all done. Have yourself a wonderful day. Talk to y'all later.
Have a good one.
Thank you.
Have a good weekend.
Have a good day.
You too.